Good morning.
Good morning, sir.
So, in the electrostatics, we are discussing the boundary value problems, which is useful when the source, like charges or potential, if it is not known in the entire region. If it is known somewhere in the region, like at the boundary or somewhere in the region, part of the boundary, then we can use this boundary value problem to calculate potential and electric field. So ultimately, we want to calculate potential and electric field. Electric field can be calculated using this relationship. So obviously, you need to find potential. So to calculate potential using this boundary value problem, we can use a Poisson's equation or Laplace equation. So if this is a Poisson's equation and Laplace equation. So Laplace equation you can use if there is no charge exist, and if some charges exist, then you can use this Poisson equation. You need to solve this second order differential equation. You need to integrate twice, and you will get the integration constants. You need to calculate the constants by applying the boundary conditions. Don't relate this boundary values, boundary condition, don't get confused with the boundary condition like a tangential component of electric field, normal component of electric field. So interchangeably we can use, it's okay. So it's like the conditions or the detail available at the boundary. Okay, so you can call it as boundary value, or when you can use, I think we used to use the word boundary values in mathematics, right? So last class we have discussed two. This class we will take one more example, or like where potential at the boundary, some boundaries will be given, and from that we will calculate the potential throughout the region and electric field throughout the region. Let us take this example. So it's like a coaxial cone, or two. You can see the center conductor, a coaxial conductor, cylindrical conductor, coaxial conical conductor, and this is the outer conductor, two conductors separated by some dielectric epsilon, and this outer conductor is kept at potential V naught, and the inner conductor is kept at zero potential, that V equal to 0. And there is a minor gap, otherwise these two conductor or these two cones will get short circuited. So these two cones, there is a minor gap. So the inner cone is represented with angle theta 1 and outer cone is represented with angle theta 2. Now first let us write the boundary details or boundary conditions given. The inner cone, that is theta 1, when theta 1 equal to the inner cone angle theta 1, it's given here, it is 5 by 10, the potential is 0, and other condition is theta 2. Theta 2 represents the outer cone or outer conductor, so theta 2 is 5 by 6, their potential is V naught, V equal to V naught, which is equal to 50 volt. So this is the detail available. So we need to start with, we need to pick the correct equation. So Poisson or Laplace we need to take. So in this case, we can take the Laplace equation because charge is not given, the charge distribution is not given, or charge is not given. Anyhow, there is no, this is a matter of capacitor here, right? So the charge is not required and it is not given, it's not applicable here. So you can take this equation, del square V equal to 0. So this is the Laplace equation. Next step, we need to decide the coordinate system. Can some of you tell which coordinate system will opt here?
Spherical.
Spherical, good. You have to use a spherical coordinate system. The reason is, see, already theta is given, right? So it is function of theta. As theta increase, like angle between one plate and other plate, or distance between the one plate and other plate is increasing by theta. Or even you can see the potential is varying by theta. So theta there in the spherical coordinate system, where spherical coordinate system you have three surfaces. One is a sphere with radius r, and theta, which is the cone angle, and phi is the azimuthal angle. So in this case, you can see clearly there is no, the variation of potential along the radial direction is 0, variation of potential along the phi azimuthal direction also 0. So only potential is varying along the theta direction. It is given in the boundary condition. It is clearly, even if you look at this details in this picture also you can understand, or else if you read this statement also you can understand dv by deta is not equal to 0, not equal to 0. Now this equation 1, so obviously there might be 3 terms, but in order to consider the variation along the radial direction and azimuthal direction, so the equation 1, if you expand, it will be reduced to 1 over r square sine theta. So this is a function of only one variable, right? So you can make it differentiation. So d by d theta into r. Can you recall this equation? Laplace equation for spherical coordinate system. You can refer here. This term you need to take, right? 1 over r square sine theta d by d theta into sine theta times dv by d theta. So it is sine theta equal to 0. So you can write d by d theta into sine theta into dv by d theta equal to 0. The reason why we are making this is if you make theta equal to 0 and theta equal to 180, this is of no meaning. You will not get capacitance effect. So that's why we are eliminating this term. So d by d theta equal to, so this will be the term. Now you need to extract, you need to find the value of v. So you first integrate one time. So if you integrate one time, you will get sine theta into dv by d theta. It'll constant, integration constant. Then again, if you integrate this equation, then you will get, or before integration, you write this equation clearly, dv by d theta equal to a by sine theta. I can write dv equal to a into d theta over sine theta. So if you integrate again, this let us say this equation 2. So if you integrate 2, you will get this equation. Let us say this is equation number 3. So if you integrate equation number 3, you will get v equal to integral, a will be a constant, so it is d theta over sine theta. So you need to be ready with this kind of integration of d theta by sine theta or cos theta or tan theta. You can refer the textbook, the solutions might be available, or else you can refer the your like a standard, if you know you can do, or else you can directly write the answer, okay, if you know the answers. So it is of sine theta by 2 cos theta by 2. You can write sine theta as of sine theta by 2 of cos theta by 2. So here you just multiply and divide by cos theta by 2 in the denominator. Then this will be reduced to this sine by cos. See, this sine by cos will be tan theta by 2. So half term is there. So tan theta by 2 into cos square theta by 2. So which will be equal to a into integral of cos square theta by 2. If you move to the numerator, it will be secant square theta by 2 over of tan theta by 2. So avoid such mathematics. You have to have at least because this topic will involve such equations, because the sign, anyhow the sign term will be there, which will come, because in the spherical coordinate system, if you go, the sign term will come. So once you have this solution for these equations, then maybe later you can directly replace integral d theta by sine theta. Directly you can replace. So equation v equal to a secant square theta by half tan theta by 2, right? So I will clean this page. Is it clear until this step? Is it correct? Okay, I will continue here. In the top space I will use. So we need to try to relate this tan and secant square theta. So differentiation of tan will be secant square, right? So secant square theta by 2 into d theta. Okay, so that equation will become V equal to A into so secant square of this term will be will happen to the term. Sorry, I think it's not off. It should be 2, I guess. Is it off? Do you remember? It should be off or 1 by 2. Sorry, off or 2. I don't remember this equation. I'm not sure about this. So you will get this like d tan theta by 2 over tan theta by 2. So it is like integration of, I'm not sure about that constant. I can check with my proper correct equation. But let me write only this part. So you can replace this secant square theta into d theta by d of tan theta. Then it is like integration of dx by x, that is equal to natural logarithmic of x. Okay. So this will give you v equal to a natural logarithmic of this term, that is tan theta over 2, plus there will be some constant, right? So we will get some other integral constants that correspond to the second integration. Let us check. I think it's the correct answer. V equal to a. Let me show the step. Oh, sorry, that is not half. That is 2. So sine theta equal to 2 cos theta by 2 into sine theta by 2. You can refer these equations. These equations are usually available in the Sadiq textbook appendix. So you can refer this equation. You need to. It's not possible to memorize all these equations. So you can refer the textbook. And the appendix, we have all required trigonometric and all the integral differential. All the formulas are available. Okay, you can refer it. So now we got the equation for potential, that is V equal to A natural logarithmic of tan theta by 2 plus B. So you need to find the integral constant A and B. Any doubts until this step? V equal to A plus B. Now let us calculate, let us apply the boundary condition. Let us first apply the boundary condition, inner boundary condition, that is at theta equal to theta 1. Don't substitute this theta 1 and theta 2 now. See guys, now you generalize it like, let's generalize the problem. Maybe in the exam, if for some other values of this theta, you can directly substitute. Let us have a generalized equation. Maybe at the final step, you can substitute these numbers. You can substitute these constants. So in the exam, probably instead of 5 by 10, it may be some other value, and this phi 2, it may be some other value. So simply now, if you have a general equation, then you can apply for any kind of coaxial cone kind of structures, right? So at theta equal to theta 1, this is theta, this inner cylinder, sorry, inner cone. Inner cone, the potential is 0, V is 0. So if you apply this into this equation 1, then 0 equal to A natural log of tan theta by 2 plus B. Therefore, B equal to negative with negative, right? So now you need to calculate. Okay, now you substitute this into equation 1. Put this into equation 1, then equation 1 will become V equal to A ln tan theta by 2 minus, see B you need to replace with this equation 2. So that is A ln tan theta by 2. See, see this is theta equal to theta 1, right? So I forget to put 1, so it is theta 1. Right? At theta equal to theta 1, so theta equal to theta 1, potential is 0. V is 0. Correct? So it should be theta 1. Now in compact form, you can write A natural log of tan theta by 2 over tan theta 1 over 2. So log A minus natural log A minus natural log B, right? So natural log of A by B. So we got equation for potential. Still, we need to find A, right? So the equation is reduced. Still, this equation carries A. So we need to find A. So now apply the other boundary condition, that is at theta equal to theta 2, potential is V naught, V equal to V naught. Okay, so if you apply this, then equation this 3 will become V will be equal to V naught. So this V will be equal to V naught. So at theta 2, right? So A natural log of tan theta 2 by 2. So this is at theta 2, right? So this theta will become theta 2 over tan theta 1 by 2. So now we have equation for V naught. Sorry, still we need to find the equation for A. So from this we can find A. So A equal to V naught over ln tan theta 2 over 2 divided by tan theta 1 over 2. Is any mistake, please highlight then and there. So now we got equation for A. Sorry, we found the integration constant A, which is V naught over ln of this ratio, tan of theta by tan of theta 1. I think now you can rewrite this equation 3. Equation 3 can be rewritten with substituting this A. So A is V naught. I will write it here. V equal to A. A is V naught over this tan of theta 2 tan of theta 1 multiplied with this term, right? That is ln of tan theta 2 by tan theta 1 over 2. See, don't think, see, this is theta. In the numerator, that is function of theta, generalized variable. It is not theta or 2. So don't get, so don't cancel this numerator and denominator. See the difference? This is theta. So now we have equation for potential. That's all. Problem is solved. So we have potential equation. Like you can call it this as like a potential at any point, like it's like any point in the space. By substituting the value theta, okay, you can find the potential. And these boundary conditions are given, theta 1 and theta 2, the potential is given. So from that we have calculated. So now what we can do is theta 1 and theta 2, that value can substitute. Like theta 1 is how much theta 1? Theta 1 is 5 by 10 and theta 2 is 5 by 6. If you substitute, then you will get simplified equation. I'm not going to do that. Let us take this as a general equation. Hope all of you got until this step. Still, we need to find the electric field. It is not complete answer. You need to substitute these two conditions and you need to simplify the answer. Simplify. So what we did is potential at boundary is given. From that we calculate the potential at anywhere in between these two plates. So next major step is this is one part of the problem is solved. Almost 70% of the problem is solved. Next step is you need to find electric field. The electric field is negative grad of V, negative gradient of V. So we are in the cylindrical coordinate system, sorry, spherical coordinate system. So spherical coordinate system, this gradient will have one d by d rho, d by d theta, and d by d phi. Three terms will be there, and you aware of that. The potential is varying only along the theta direction. So we need to retain only that term, theta term. So that is will be 1 by r into d by d theta into v. So del will be equal to 1 over r into d by d theta, right, multiplied with the scalar v. So you need to differentiate this equation, let us say equation A, with respect to theta. But it's very, looking at equation A, it's going to be complicated, right? So differentiating by theta, that will involve the natural log, is not going to be an easy thing. So instead of that, while solving the capacitance problem or the boundary value problem, wherever you find this dV by d theta, see that's required, dV by d theta or dV by dr or dV by dz, it may be required. Okay, the potential variation along some coordinate, x or y or z, okay, or rho or phi or theta. So this term probably, see, not probably, it should be there already. See, we have already calculated this term dV by d theta, because you have initially you have the second order differential equation, right? The del square v equal to 0. So after integrating one time, you got dV by d theta term, right? So you can use that equation dV by d theta. Already the term was there, so you can use that term instead of differentiating equation A. You can use this term dV by d theta, because why we are doing that is we have started with the second order equation, differential equation, then we have integrated it first time. After integrating to first time, you will get the first order equation, right? First order differential equation. So that equation you can reuse here. Okay. Now let us check in this page. It's not available in this page. I think that's deleted. I have deleted. Can anyone tell what is the value? What is the value of dV by d theta?
Sir, I think it was A upon sin theta.
Yeah, repeat. A upon
Sin theta. A upon sin.
sin theta. Right? One thing I forgot. This is vector, right? So it will be along a theta direction, right? So it should be along the a theta direction. So dV by d theta is a by sin theta. I think this is what the after first integration, this is what the equation we had, right? A by sin theta. Now, you know, let's keep 1 by r. And what is a? So we need to only substitute a, right? So the a you need to substitute, that's all. So if you substitute a, it will be v naught over ln tan theta 2 by 2 over tan theta 1 over 2, right? That's all. I think sin theta term I have missed, so multiplied with sin theta. So sin theta term will be, there is no space, so just I will put a s here. So sin theta multiplied with this term. So this will, I got, that's all. We got the equation for electric field. Okay. So I think there is no space available. I will explain you with the direct equation. So first we got the equation, general equation. After solving this differential equation, we got a and b differential, sorry, the integration constants. Later we have calculated a and b. So first we got integration constant b. Then we have calculated integration constant a. Then this is what the equation, general equation, or it's a function of space, the potential you can calculate. Okay, so general equation, and you can see as discussed in the last class, you can verify v should be function of only theta. It should not a function of theta, or sorry, it should not function of phi or rho. It's correct. Okay, next step you need to integrate this. Sorry, you need to differentiate this. So this is what we did. So this dV by d theta is a over r sin theta, sorry, a over r, sorry, a over sin theta. I will highlight the previous slide. So this is what we are talking about. dV by d theta. So it's in the next step, right? So a by sin theta. So we will replace, we will use this. You can directly use that, so that we can avoid the complicated differentiation. So if you substitute, then we will get the equation for potential, sorry, electric field. So later, if you substitute, you will get this equation. Now let us not do that. Let us only let us stop at this step itself. So we get electric field equal to you can see minus a theta. Like electric field is along the negative of a theta, right? Negative to the theta direction. Let's check. Is that correct? See this. You can see this is at lower potential. This is at lower potential, right? This is at the higher potential, or you can say V1. This is V2. So V2 is at higher potential and V1 is at the lower potential. So electric field will be from higher to lower potential, right? So like this. So electric field lines will go in this direction. So it's not radial, it is theta direction, right? So it is in the opposite to theta, positive theta. So you can say electric field is along the negative theta direction. Clear? So please, once you got the answer, please check. Potential should be a scalar and electric field should be a vector. That's a known thing. But by any chance or by mistakenly, if you keep some vector, unit vector there, or if you forgot to include the unit vector, maybe even at the last stage you can add this. If any clarification required, please speak.
No, sir.
Thank you. Then we can move to the other example. No more exams related to this. We can switch to other topic. So in the boundary value problem, we have applied to calculate electric field and magnetic field. Sorry, electric field and potential. So what boundary condition or detail is available is potential at the boundary that's available. Now we will use the same problem to calculate the capacitance. See, it is like even in this case, you can see two plates separated by a distance, right? Some gap. So we can calculate with this form capacitance. Two plates carrying equal and opposite charges separated by a short distance. That's capacitance. So we can use this problem. We can solve the capacitance problem also using the boundary value problem. Okay, so we will start with parallel plate capacitor, then we will go with the spherical capacitor, then coaxial capacitor. So we will see how to apply this boundary value problem to calculate capacitance due to any structure. So we will start with some basic structures like a parallel plate, coaxial, then spherical. So these capacitors we will discuss. Then we can take some arbitrary shapes, some complicated shapes that we will do it in the next class. So this class agenda is we will start with some basic structures. Now let us see the procedure. So calculating the capacitance using the boundary value problem approach. So this is obviously the C equal to Q over V equal to E dot dl. So if you know electric field, see obviously from the potential you are going to calculate electric field. If you know the electric field, you can calculate capacitance. How to calculate capacitance? The flow is here. C equal to Q over V, and you can calculate V from the electric field. Or if V is directly given, you can take no issues. Okay, so the denominator if you push, then you will get the equation for capacitance. So what required is you need to know what is the Q, what is it, Q and V. That you need to calculate Q and V. Now let us see how to calculate this Q and V in the boundary value problem. Is the negative sign, read this statement, negative sign should be dropped because we are interested in the absolute value of the potential. So you can drop here itself. Now let us see the method to calculate the capacitance. A lot of text might be there, but nothing. The approach is such a simple one, simple approach. Calculating the capacitance is simple approach. See, two ways you can solve the problem, or two ways you can use this equation to calculate the capacitance. In one approach, see, C equal to Q by V, right? So numerator, denominator. So in one case, numerator you need to assume, and denominator you need to find. That is one approach. Other approach, denominator you can assume, you can take some value, you can initiate some value, and you can find the numerator. Okay, so it's a ratio. maybe numerator can assume or denominator can assume, and you can find the other value. So two approaches are there, and we will, if you take this first approach, what is assumed? Charge is assumed, and you need to find the potential. So in that case, you can use the Gauss's law or even Coulomb's law you can use. So charge enclosed equal to the flux leaving the closed surface, d dot ds. Okay, so from that the q can be, sorry, not q you have assumed, right? So this side you have assumed, this side you have assumed. So you can calculate the electric field from this equation. See, d equal to epsilon e, and you can calculate v e equal to negative gradient of v. So that way you can calculate, or even you can calculate e equal to, sorry, v equal to e dot dl. Right, I'm repeating this step. Okay, many of you will solve, you're going to solve one problem. Huh? So two approaches are possible. One is with, you can use Gauss's law, where you have to assume the charges, and there is other approach, you can use Laplace equation. So you see here you are using only Laplace equation, Laplace equation, but here we will assume the potential v equal to v naught or some value depending on the boundary we will take. Anyhow, we are not going to take this. We will consider only the Gauss's law right now. If time permits, we can discuss some problem based on the Laplace equation. Now let us focus only on the first approach, because first approach why I'm taking is that's easy, because already you are aware of Gauss's law. Applying the Gauss's law is such a simple problem. Now let us see the procedure. So first fix the coordinate system, then find v, then c equal to q by v. That's all. Now let us take one example, then you will understand this procedure or the steps very clearly. Now consider this parallel plate capacitor. It's along the x-plane. At x equal to 0, one plate is kept. At x equal to d, other plate is kept. And this is plus positive charges deposited on one plate and equal negative charges deposited. So electric field will be from sorry plus 2 minus. Right. So you need to calculate C equal to Q over V. Right. Now we have to find Q. You have to assume Q. So Q equal to, how will you calculate Q? Q can take Q, right? Q is the amount of charge in the top plate, or Q is the amount of charge in the negative plate, bottom plate. So no need to even calculate anything, right? Q can assume. Q is the charge on one plate, total charge. Now you need to calculate potential. Okay, so to calculate potential, you need to use this equation, Q equal to, sorry, V equal to negative E dot dl. See, the problem is now we need to know what is E vector or electric field. Okay, now let me write like this, then you will understand this clearly. E vector, sorry, D equal to epsilon E. So E equal to D over epsilon, right? So D over epsilon dot dl vector. Now you need to calculate D vector, that is electric flux density you need to calculate. So electric flux density in the capacitance. What is the electric flux density due to this capacitor configuration? So for that, as suggested earlier, you can use Gauss's law. You can use Gauss's law, or it's again you can very easily calculate. If you take any plate from the boundary condition for electrostatics, electric flux density will be equal to rho s, and that will be perpendicular to the boundary, right, or the plate which is carrying the charges. Hope you recall this. dN equal to, or electric flux leaving a surface equal to rho s. So this is actually easiest approach. Now we can generalize this D vector equal to, for this problem, if you take any point in between these two plates, so D vector is rho s. Rho s is the surface charge density in maybe in the top plate or bottom plate, any plate you can take. If you take the top, it is positive charges, then direction of electric flux is going in the negative direction. So it is in the negative direction, minus AX. Do you understand this? How I am writing this? This is from the boundary condition equation. Boundary condition, you have two equations, right? E tangential component, ET1 equal to ET2 and dN1 equal to dN2. And if there is one side, if it is a conductor, then dN equal to rho S. This is for the conductor and the dielectric boundary. So d vector is rho S into A minus AX. Hope you understand why it is minus AX. If you take positive charge, then electric flux will go in the negative X direction, right? Negative X direction. Or if you take a negative charge, then electric field will go in the positive X direction. Any this negative sign will be there. The negative sign will be there. So now V equal to, now this we can put it this into equation 1. See, here we have not used the Gauss's law. Understand? We are not used the Gauss's law because this is even quite easiest way to calculate. So we can avoid Gauss's law here, right? So V equal to equation 1 you take negative d equal to rho S into AX. So already there is a negative sign, minus and minus will become plus, rho S over epsilon AX cap dot dl vector. What is dl vector? What is dl vector? To find the potential, you need to find the tangential component of electric field. So electric field is along this direction, right? This direction, right? So you need to do the differentiation along the x direction. So it is dx into AX. And what should be the integral limit? Integral limit is from 0 to d. Right? From 0 to d. So if you integrate, you will get rho S epsilon. Then AX dot AX will be 1. So integral dx. Integral dx. What is the length? What is this length or gap between these two plates? It is d. Right? And now we can substitute this. Let us say this is equation 2. You can put this into equation A, general equation. So C equal to Q over V. Q over, what is V? V equal to rho S into D over epsilon. What is rho S? Can you write this rho S in terms of charges? So rho S is coulomb per square meter. That is the surface charge density. Surface charge density, coulomb per square meter. So rho S, then rho S will be equal to total charge or charges per area. Area, let us take A is the area of the plate. Let us take A or S is the area of the plate. Okay, then you can replace rho S with Q over A. So then you will get Q over A. Already D is there and epsilon is there. That is then this Q and Q will get cancelled. Then you will get epsilon A over D. So you got the standard equation C equal to epsilon A by D. Where like how the structural parameter decides the capacitance in terms of permittivity, this gap, area of the capacitance, right? So the procedure is quite simple. We use this equation. So where we really applied this boundary value problem is at this point. At this point, we have applied the boundary value problem. Again, don't get confused with this boundary value and that boundary conditions. But anyhow, it is like at some boundary, if you know some details, that's called as boundary value problem. So in this case, you know what is the electric flux here, right? So instead of using Gauss's law, you can use this approach to calculate the electric flux. Any questions? So all problems, you have freedom to use Laplace equation or that is second approach. First approach, you can use this kind of approach like Gauss's law or Coulomb's law you can use. So please go with the first approach. It's quite easy. Now let us consider for the coaxial capacitor. Coaxial capacitor, it is like there is a center conductor which has positive charges here, right? So negative charges in the outer conductor, outer circular tube. So electric field will be from positive to negative. In this way it will go. So you need to take the cylindrical coordinate system. Let me show step by step. If are available here, you can directly take. See, C equal to Q over V. You need to calculate the V or V. How will you calculate V equal to? Okay, let me. C equal to Q over V. Now let us apply Gauss's law. So before that, you write here Q over E dot dl, right? So we need to calculate E vector. So to calculate E vector, you can use the Gauss's law. Already Gauss's law we have applied. We know we have applied the Gauss's law to calculate electric field from infinite line charges. Same equation you can put here if you recall. Otherwise, now let us rewrite write the equation again. So total charge enclosed equal to d vector dot ds vector. It's a general equation for Gauss's law. Okay. Now you need to construct or you need to find the total electric flux leaving from center conductor and it is terminating at the outer conductor. So you need to consider or construct a Gaussian surface. Gaussian surface. Now let us take the Gaussian surface. Radius is greater than a and it should be less than b. This should be the Gaussian surface like this. You need to construct. Now you can calculate the number of lines passing through this surface. That way you can calculate the total flux. Okay, so Q enclosed equal to D equal to epsilon E, right? So D equal to epsilon E vector dot ds vector. And what is the surface area? See, all these vectors will pass through the surface area or it will be normal to the surface. So what is the surface area of the cylinder? So it's epsilon E into, what is the surface area of cylinder? 2 pi rho is the radius and L is the area, L is the length. 2 pi rho into L. L is the length of the cylinder. See, here we are calculating only the curved surface area only. We are not calculating, see, I will highlight here. So this is a cylinder you are constructing. You are calculating only the surface area of the curved surface. You are not calculating the surface area of the top and bottom plates. The reason is electric field is going to pass through only the side walls, right? It's not going to pass through the top and bottom. So that's why we are only considering the surface area of this curved surface. That is 2 pi radius multiplied with the height. Is it clear? So this will be the total charge inflow. So from this, we can write the equation for electric field. So electric field equal to Q over 2 pi epsilon rho into L. Have the equation, right? So you got equation for electric field. So electric field now, if you write it as in terms of vector, so E vector, it will be along the path radially outward, right? The electric field is starting from the or originating at plus and ending at terminating at negative. So it is in the plus arrow direction. So as per this configuration, it will be radially outward. So it will be arrow cap. So next, we can put this into equation 1. Sorry, equation A. This equation A will become C equal to Q over E vector dot dl vector. E vector is Q over 2 pi epsilon rho L into A rho dot d rho into A rho, because we need to integrate along this direction, right? Radial direction. So d rho into A rho. What is the integral limit? What is the integral? A to B or B to A? It is from A to B, right? So lower limit is A and upper limit is B. So we will get Q over the denominator, this Q 2 pi epsilon L, all these will constant. So what remain will the integration, it will be A to B d rho over rho. this q and q will get cancelled, right? And this 2 pi epsilon L will go to the numerator. So 2 pi epsilon into L over integral d rho by rho is natural log of rho. Okay, so ln see, if you want to remove this negative sign, you can reverse this integration order. Then it will be from see, if you make it positive, just we are reversing it to B and A. You can swap this. Okay, so ln A by B. That's all. So this will give you the equation for capacitance due to coaxial capacitor configuration. Same you can calculate for other structures. Process is only you need to calculate potential. To calculate potential, first you need to calculate electric field, then you can calculate potential. That's all. Is clear? Any questions? Okay, next class we will take a few problems related to the capacitance calculations. We will take some arbitrary geometry or some other than this kind of general geometries we will take. Then we will calculate the capacitance and we can wind up this particular topic. So before leaving, one more, a few days before I have shared one notification regarding the recruitment for IEEE EMC Society student branch chapter. Actually, a couple of weeks before, I have circulated one Excel sheet where some considerable number of you have expressed your interest. That's fine. I have collected your interest. And later yesterday, I think 2 days before, I have floated a form. Again, you need to fill this recent form. Even though already you have filled that form, again, you need to fill this form to attend the interview. So actually, yesterday one schedule was done, and other schedule is this coming, I think Saturday or Sunday. The date is not fixed. So if you are interested, use the recent link, Google form link, posted in the Teams chat. I think that's the recent chat I had I made in the Teams. Okay, you can use the chat. Or you can take part in the recruitment, and if you're interested in technical activities, then there are some positions also available. If you're interested, you can take part in the board. Any questions? Okay, if there is no questions, you may leave now. Thank you.